Hello everyone and welcome back. So last class we were discussing about the mass transfer losses, and we saw that even if we increase the flow rate of fuel, that is, let's say we go from 1 lpm to 2 lpm or to 3 lpm, we don't intend to generate infinite amount of current no matter how much fuel we supply, and that is primarily because it is the fuel cell performance is hindered or rather limited by the individual material resistances. For example, if we have a better catalyst, we will have minimum loss there, but we cannot say that there will not be any losses. There will be some losses. Of course, coming on to the ohmic resistance, it is again characterized by the resistance of the electrolyte itself. So even if we have even the good conductor of ions in terms of electrolyte, we still have the ohmic resistance there, and that is why we will not be able to draw infinite amount of current here in this case. And as we can even see, in case of this 1 lpm, we have this fuel efficiency, as we have already seen that it is the fuel required to the fuel supplied. So since the mass of hydrogen that is actually supplied is increasing, no matter what is the current drawn from the cell, the fuel efficiency will eventually decrease. That will again decrease the overall efficiency of the cell. So moving on, let's come back to our Nernstian losses. So coming back to Nernstian losses. So we know that it is the Nernst potential is basically sum of reversible potential and the incremental potential that is observed with the activity logarithmic ratios of the activities of products and the reactants. So activity of products to the activity of reactants. Please, we need to understand is that this is the equation that we wrote assuming that there is abundant supply of reactants at the the reaction sites, or in other words the bulk concentration of the fuel and the oxidant is infinite. However, when we draw the current from the fuel cell, the available concentration of the reactants at the reaction site is different than what is supplied in terms of bulk concentration. So this we cannot write anymore in case of when we are drawing more current from the cell. So let me write this up. So this equation is valid when bulk concentration remain same throughout the cell, right? So that is the channels to catalyst layer. So this bulk concentration is assumed to remain same throughout the cell, which is not the case when we draw higher amount of currents. So as the current increases, so as your current increases, the concentration of the reactants is not equal to the reactant concentration. So Cr is not equal to Cr star, and therefore En is no more equal to En star, where En stands for the Cr, where En star stands for the Cr star. So for simplicity, let's only focus on the reactants. So let's write that, let's focus only on the reactants. So let's write this concentration, eta concentration due to Nernst potential is basically difference in the Nernst concentrations En star. So let's write this up, E naught minus RT by NF ln of 1 by Cr minus E naught minus RT by NF ln of 1 by Cr star. So if we simplify this, this comes as RT by NF ln CR by CR star, and as we know, since CR is equal to ZL delta by NF D effective, so we can write CR star is equal to CR minus J times delta divided by NF D effective. So that implies CR star equals ZL delta divided by NF D effective minus J times delta divided by NF D effective. Let us take the common terms out. So, and let us write for CR star by CR, which is equal to this CR star is again let us J delta ZL delta by NF D effective minus J delta NF D effective whole divided by CR. CR is ZL delta divided by NF D effective. So that implies CR star by CR is equal to ZL divided by ZL minus J. So that implies eta concentration due to Nernst potential is equal to RT by NF ln ZL by ZL minus J. So if J is very less than ZL, which is limiting current density, this eta concentration due to Nernst potential will be very small, However, as J approaches ZL, so in other words, when we start drawing more and more current and try to reach towards the limiting current density, this eta concentration due to Nernst potential will increase sharply. We have one more reason for the mass transfer limitations by reaction rate. So let us write that concentration due to, this is concentration loss due to reaction rate. So let us recall our Butler-Volmer equation. So Butler-Volmer equation is J equals J naught CR 0T by CR e to the power 1 minus alpha NF eta by RT minus CO 0T divided by CO e to the power minus alpha NF eta by RT. So in other words, the current that is drawn from the cell depends highly on the reactant and product concentrations. So let me write these words. So reaction kinetics depends highly on concentrations of reactants and the products. So when we are drawing higher current, so we have to, so while drawing high current, we can write the same Butler-Volmer equation as J equals J naught, only forward current and the term corresponding to the forward current will be dominating this difference. So that is basically CR 0T divided by CR, and this is into the 1 minus alpha NF eta by RT This we have seen as CR star. So we can write activation or potential as RT by 1 minus alpha times NF ln of J by J naught, and this activation over potential can also be written in terms of the concentration of the species. So which can be written as eta activation RT by 1 minus alpha NF ln. Now J, which is the actually the current drawn from the cell when we are supplying or when we have CR star as a concentration of species available at the reaction site. So we can replace this J by CR star, and J naught is again the exchange current density. So let us write this as CR. So let me write this as, however, we like to know how much of eta activation changes with respect to available concentration, that is CR star basically. So we know this available concentration is equal to CR minus CR star. So let us write this eta activation star, which is RT divided by 1 minus alpha NF ln of CR star divided by CR minus CR star. So what is the change? Change in activation over potential is eta concentration due to Butler-Volmer equation is basically eta activation star minus eta activation. So let us move on to the next slide. So let us substitute for eta activation star and eta activation. So it is RT by 1 minus alpha NF ln of CR star by CR minus CR star minus RT by 1 minus alpha NF ln of CR star by CR. Let us simplify. So it is RT by 1 minus alpha NF ln of CR by CR minus CR star, right. So we now need to replace this concentration of reactants, that is CR and CR star, with respect to corresponding current densities. So let us replace this CR by and CR star. So we can still write the same equation as RT by 1 minus alpha NF ln of JL by JL minus J. Now the reason we have replaced CR by JL is because the CR is as we know is a bulk concentration, and that actually corresponds to what is the maximum current that we can draw from the cell, whereas CR star is the concentration that is available at or that is basically consumed at the triple phase boundary. So that corresponds to what is the actual current that we are drawing from the cell or the current density that we are drawing from the cell. So that is why CR star is very much related or proportional to J, or let me also write this or say this as J is proportional to CR star and JL is proportional to CR. So let us move ahead. So we can write this final concentration, eta concentration is basically sum of both of these concentrations or rather mass transfer losses from arising from the Nernst potential as well as the Butler-Volmer equation. So we can write this as RT by NF ln of JL by JL minus J plus RT by 1 minus alpha NF ln of, again the same term will come here, Jl minus J. So, if we take this common term things out, it is basically 1 plus 1 divided by 1 minus alpha ln of Jl divided by Jl minus J, which can be written as the concentration is C times ln of Jl divided by Jl minus J, where C is constant. So, in other words, if I try to draw how respective overpotentials change with respect to current drawn from the cell. So, let me write this is current drawn from the cell. Let us just focus on fuel cell first. So, let me write this is mod of overpotential. So, how does the actuation overpotential change? So, it increases initially and then almost remains constant. There is not much change that we can observe. So, this is eta activation. Coming back to the ohmic overpotential, which is very linear, as we have seen, eta ohmic is equal to I times R ohmic. So, eta and I are directly proportional and they are related by the ohmic resistance. So, it is very linear, as we can see, it is a straight line. However, in case of mass transfer losses, as we know, it is a logarithmic relation between the concentration loss and the current that is drawn from the cell. So, initially the mass transfer overpotential remains slightly low or minimum. However, as and when we start drawing more and more current, it increases exponentially. So, this is nothing but JL. So, as and when current density approaches the limiting current density, the mass transfer overpotential, this is eta mt, it increases exponentially. Sum of all these three losses, basically, which when we add them up and subtract from the available energy, that is how we get the characteristic curve of the fuel cell. So, let me write this up. So, for fuel cell, this E operating potential is basically E naught minus eta activation minus eta ohmic minus eta mass transfer, and this reversible cell potential is typically replaced by the open circuit potential. So, I can write this E operating, that is operating potential is nothing but E OCV, which is typically 1 volt in case of low temperature hydrogen oxygen fuel cell, minus this 3 resistances or 3 overpotentials, ohmic minus eta mass transfer. And as we know, in case of fuel cell, this eta is E naught minus E, which can be written as E OCV minus E, and E is E operating potential. This is in case of, and this is positive in case of fuel cell. However, the same thing, E naught minus E, this is E operating, this is negative in case of electrolyzer. Since the operating potential is more than the reversible potential, eta is negative in case of the electrolyzer. So, let us draw this up. So, this is EOCV or the open circuit potential, and the reason why we get curved like this is because at any instant of time we have all these three overpotentials. We need to add them up. So at any given time, at any given instant of time, this eta is sum of three overpotentials, and this eta is nothing but this is the drop that we discussed. So when we are operating very close to the open circuit potential, or in other words, when we are drawing very small amount of current from the cell, the activation overpotential dominates. When we draw the current from the cell, which is moderately high, then we are in the second zone and wherein the ohmic overpotential dominates. And when we try to draw maximum current from the fuel cell, then when we approach this limiting current density, we can see that the mass transfer overpotential dominates among the three. Let's quickly solve an example. So for fuel cell, which is H2O2 fuel cell, which is operating at STP. The 3 points given, 0.2, 0.5 and 0.8, these are the current densities. Limiting current density is 1 amps per centimeter square. This is also amps per centimeter square E. So let's find out the mass transfer overpotential, or in other words concentration overpotential for three different points. This is 0.1, 0.2 and 0.3. So let's first write the concentration overpotential is basically RT by NF, 1 plus 1 minus alpha ln of ZL divided by ZL minus J. Right. Let's substitute for point number 1. Current density is 0.2 amps per centimeter square. So concentration losses will be, we know RT by F is 25.6 millivolt. So N is 2 for hydrogen oxygen fuel cell. This is, let's take alpha as 0.5. So this becomes 3. Ln of ZL is 1 amps per centimeter square, 1 minus 0.2. So this comes close to 8.55 millivolt. This is the first case. Second case, where J is 0.5 amps per centimeter square. So eta concentration is again 25.6 millivolt divided by 2. 1 plus 1 divided by 1 minus alpha. This, if we substitute alpha, this becomes 3 ln of 1 divided by 1 minus 0.5. This comes close to 26.61 millivolt. And let's find out for the third case, when J is almost reaching the limiting current density per centimeter square. So eta concentration is again RT by F, which is 25.6 divided by 2 times 3 ln of 1 divided by 1 minus 0.8. So this comes close to 61.8 millivolt. So if we try to draw the concentration losses with respect to current density, as we can see, they will increase slowly, and if this is our limiting current density, they will shoot up as and when we draw more and more current. So to avoid these mass transfer losses, to avoid, or rather I should say minimize the concentration losses, eta concentration, the reactant concentration, the reactant concentration should be enough in substantial quantity at the reaction sites. Okay, so this is the first point. And how we do this? So that is why, so to achieve substantial quantity, or to have enough quantity of this concentration of reactants at the reaction sites, we should have this concentration convective flow of species should be better. In other words, if we have a convective flow of species, as we have seen this before, the diffusion layer thickness decreases with the increase in the convective flow of the species, and if the delta decreases, as we have seen, the current density, limiting current density will also increase. So that is why this convective flow of species is a better option, and this is one of the reasons why bipolar plates, therefore bipolar plates, or bipolar plates in case of stacks and monopolar plates with better flow designs are preferred. So what are these better flow designs? We have serpentine flow field channels, we have parallel flow designs, we have interdigitated flow designs, all these things which of course we will discuss. So these designs basically, they help this reactant species distribute uniformly on the surface of diffusion layer, and that is where they get diffused through diffusion layer and reach the reaction sites. So if you want more and more reaction sites to be used, or in other words, if you want more triple phase boundary to be utilized, we should ensure that this reactant species reach the respective reaction sites effectively, and that is why distribution of this species using dedicated flow designs becomes very important. So let me explain this. So we have I only explain the one half of the cell. So we have these designs. So this is our monopolar plate. And this is our hydrogen, and this is our diffusion layer. This is our electrolyte, this is anode with GDL, and this is our bipolar plate or monopolar plate in case of single cell. So somehow we bring this hydrogen to the flow channels, and it is also taken out. Unused hydrogen also taken out from the bipolar plate. So as we understand, these bipolar plates are directly in contact with the diffusion layer. As we can see here, they are directly touching the diffusion layer. So electrons basically move towards GDL, or they move away from the GDL towards bipolar plate, depending upon which compartment we are talking about. If it's hydrogen side, in this case the electrons will jump from diffusion layer towards the bipolar plate. So we have to have some desired properties for the bipolar plate. Let me write this up. So electrons jump from GDL to bipolar plate. So in other words, bipolar plates are the ones that conduct the electrons receive the electrons from GDL and then transfer it to the current collector or to the external circuit. So, desired properties, therefore, the desired properties of bipolar plate, first it should have very good electrical conductivity, should have very high electrical conductivity, second it should also have very high thermal conductivity, we will discuss more about the thermal conductivity and its significance as and when we discuss about the scale-up issues. Third, it should have a good mechanical strength. Why it is important? Because the bipolar plates on the either side, they are the ones which hold the entire assembly together rather firmly, and that is why they should possess a very good mechanical strength. They should also have good corrosion resistance. So, when we say good corrosion resistance, why it is important? Because as we can see in case of particularly the low temperature PEM based fuel cell, wherein the proton is shuttled from anode to cathode, the pH of this entire system is very low and it is highly acidic in nature. The entire system is highly acidic in nature, and that is why the bipolar plate surfaces are very prone to corrosion, and in order to in order to basically prevent the performance from losing because of the corrosion issues, we should have a good corrosion resistance of the bipolar plate. Should be lightweight. Almost 60% of the entire fuel cell system is basically governed by the weight of these bipolar plates, and that is why it should be lightweight because if we are aiming for space applications or unmanned aerial applications or let us say drone applications, as we understand, more is the weight of this source, more will be the the dead weight carried by these vehicles, and that is why it should be lightweight, so that the gravimetric power density of this fuel cell system will be higher. Ease of manufacturability, ease of ability should be very easily manufactured, and last but not least should be cost effective. So, we will stop here and we will take on with the more on bipolar plates in the upcoming sessions. Thank you.